Hello, people. Um, I have a follow up on my last post about handlebars and such. Um, I just got finished writing the blog post about it. We're harking to Master and Commander, that killer film that most people should see. Um, but the reason why is because I'm going to talk a bit about master part modeling in this. Okay, so when I did the last video, I realized after the fact that I had not really cleaned up my fundamental model of my handlebars. I had made a calculator. I had modeled a tool. I had done a lot of good work, and the handlebars themselves looked great and exactly what I'm trying to do. But what I was seeing when I was reviewing the video is that I hadn't gone back and updated the model for the handlebars to be in accordance with how I do things now. The model for those bars are several years old, as seen in that video, and I kind of couldn't live with the fact that I had left that out there and haven't really talked about this. So, and I write about this in a post, Accountability Mechanisms, and here it's from March of 2024, and I talk about the various types of accountability mechanisms we might have that force us to do better work, right? And, one of the things that forces me to do better work is, it's a bit pride, but like I want to demonstrate, let's say, my best work, not my phoning it in work when I'm presenting on my web page or in a video. So that forced me to go back and really sink my teeth again into handlebar geometry and modeling and everything like that. This time, instead of trying to get to a point where I could have the tool made or a calculator made, really update the essential model for the bars. And I do that. And in the post, I talk a lot about or in the current post, I talk about master part modeling. And if for people that aren't used to that, let's switch over to SolidWorks. Here's a drawing of the handlebar assembly. You can see here that I've got a master handlebar stem equations and geometry, and that's effectively my master part. In the case of this assembly, I'm using that master part, let's go to some mates here, to hang all my parts onto. All right, we've got a couple configurations here. Let's see if this one updates. Let's do align to frame for an all road. I'm pretty sure this updates correctly. I probably should have checked. There it goes. So I have my rise bars, I call them. So it's gull wing versus rise, and these are rise. Because I'm bridging between and I'm using these separable struts largely to get some height from where the top of the head tube is. You can see here I've also got my my bar in here, and actually I need to go back and update the bar in file to use this master part, because that'll do a huge amount to help me align that. Because if you look, I don't know if it's going to be visible here, the shape of this bar in relies on understanding the bar geometry and the frame geometry and some other stuff. So I'll be updating that next, probably when I do the second generation of those. But let's go to align to frame for my current bars. Now, of course, oh, this might fail, but let's see. Now these are for my custom bars, but you know, I have configurations for other handlebars here. Okay, here we go. So here's a traditional, or what we'd call a commodity stem and bar. These bars, there's some sort of error floating around. Oh, in the stem, probably some fillet thing. But this is an SQ Lab 30X low 16. So I have some very specific information about this setup. And this is used in my larger, you know, full assembly models so that I can understand position. Um, there you go. So you can see what happens when we use this setup. Um, it's very important in custom frame building that we know this cockpit information very precisely. I'm going to go back. Let's do a line to frame. I like a line to frame because it kind of is how it sits on the bike. Okay, so let's bounce over. We're gonna close that down. So I just said that there is for hanging parts onto. But right here, this is our weldment, and this comes into this assembly all set up because, of course, when we're working in that environment, we want to know, you know, how everything fits together and is cut and everything. I've got a printed part here that needs to be modeled. I've got these struts that are very complex in how they meet, and it also has to be very specific how they meet. Like that's part of what drives this level of modeling, is that if I'm off just a little bit in terms of the placement or cut of these struts, the it's going to be really obvious really quick, either in terms of how the scallop is centered looking or the height on the binder. And you can see I haven't left a lot of room on this binder with these bent pieces here. When does this come up and when is it valuable? Oops, there we go. Well, you know, here's my fixture setup that I discuss. Here's that a drawing. We'll talk about that in a bit. But I need to be really precise. And again, the reason why I spend so much time on handlebars and the geometry of the handlebars is because they're so critical in getting the bike right. And when I'm doing unitized bars and stem type systems, that has to be dead nuts. I mean, we're talking about just from my perspective, in material costs and painting costs or powder coat costs. You know, we're talking about a $200 subassembly, you know? So I don't want to screw that up. And I don't want to go back and have to make it over and over again because I got it wrong. So I have done significant work in this space to ensure that that's true. Okay, let's take a look at this again. Again, we have our master part here, and this is again being used in this subassembly. And let's say we can have our, let's show that. So coming in to mate to these struts, we've got these axes for the hand grips as defined by the master part. And that's all getting mated together. There isn't anything too crazy going on yet because we're just building an assembly so far, right? I have geometry and, well, let's dig deeper. Well, no. Let's do a survey of its use and then we'll dig deeper, even though that's opposite of what I do in the post. So I've got various parts. I've got my left lug and my right lug and my crossbar. Let's look at the lug, okay? Now, this lug is effectively a bent, I use a, we can talk about this. I use some very specific geometry, of course, for there we go, the bend there, and I have an axis there. But I'm actually, instead of just sweeping along a sketch, I'm actually using 3D geometry for that bend, and I actually mathematically calculate the beginning and end of that bend, and I do that in the master part. Or do I do that in the master part? I might do that here. But it describes, oh no, I do it in the master part, yeah. But because this has real value when we get into especially rear end bike geometry, where the beginning and end of a bend is, and the exact placement in 3D space. So by mathematically solving that, I can do a lot more calculation and then build it using the math rather than a sketch. But here, let's look at that. We'll go to edit that feature. And if you look, that plane in that part, that is bent segment angle plane, is defined by gull wing, strut, axis, end, blah, 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 from the PVD master handlebar equations and geometry part. Well, that's interesting. That's how I define the geometry within this. Okay, let's look. And actually, let's bring it out to a full tube at this point. Okay, so there's the raw tube. Of course, we're using rational descriptions within the part. If you look at the origin is right there. Let's call that the sensible origin. It could be anywhere on this, but it's not in some goofball location out in space. But if you look here, we've got a part in our part, right? We're at a part level model, and we've got this, well, this is the master part, and coming in with that is surface bodies, solid bodies, although I don't have any solid bodies coming into this, axes, planes, and coordinate systems. And then I've mated that to our origin, aligning the axes. And you can see coincident origin, and then UCS handlebar inside and left from the master part. And that's where we're getting most of this complex geometry, okay? We're gonna go down, we'll finish the part here. Okay, here we go. So I've got these two goofball cuts. We look at it from here, and well, these aren't aligned in any way. You know, these are weird cuts. You can see that this face here isn't a round profile. It's got another segment attached to it. And that, of course, in this case, is a surface cut. Oh, not that one, not that one, that one. That's a surface cut. Okay, let's go back to that, right where we did it. And I'm going to edit that feature. What am I doing? In the PVD master handlebar equation geometry, blah, 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 I'm taking front-facing binder surface. So in this case, the bolts are facing the front. You can see this surface. Let's go into our part, and we can show that there's a... let me close this down. I'm using a surface to do a cut. Let's show these two different surfaces. So there's one surface that's just a shape of a paragon binder. Here's another one with it facing in the other direction. So I can choose which one I'm cutting to. And in this case, I'm doing front facing, which is not that one. So let's hide that. So you can see this odd arrangement is producing a real cut. Now, yeah, we use hole saws when we cut these tubes in a manual environment and everything like that. You know, if you have laser, you don't have to. But for most of us, we're going to be using a hole saw, but this part of it is a round profile, and this part I can, when I'm cutting, mill that section off with like a second hole saw pass and an offset. Let's do that. And let's go to this cut here. Well, there's a sketch for that cut, sketch 6, and we'll look at the sketch plane, handlebar sweep plane. So of course our handlebars are largely defined by what the sweep angle is. Handlebar sweep plane right here, and you can see that that is not aligned with the bend, or the, let's say, the base part. That's a cut into it. And if I look at what's defining that, I'm doing handlebar sweep plane from the master part and everything. Well, that's really simple stuff here. I'm just redefining a plane, and this is a part that I should probably bring up in my blog post about how we bring geometry into parts from the master. You can just draw on the plane as it exists, and we can see all the planes here from the master part, and we could just draw right on that. And if you look here, I've just made a new plane in the part. This is a cumbersome, I'm adding some cumbersomeness to this, and this gets into when we change the master part, what happens to the file. Because if you're basing everything on the master part, you change the master part, suddenly the whole file blows up. And then there is a certain level of commitment that's involved in going to this method, because if you just kill the master part or something like that, you're going to have some issues. So I think in just quickly running through the scenario in my head, if I'm getting rid of a master part, what I should be doing is suppressing that master part in some way, setting up my geometry, swapping out the master part, and then reattaching that geometry. But for right now, it's pretty good, and you can see that in terms of this, I could have just cut to the chase here, is that's referring back up to here. It's a nice feature within SolidWorks. So you can see that this bent segment plane, this bent segment axis refers to this plane and this plane. I make an axis. And that's another weird limitation of SolidWorks, where I can't, even though I have this axis in here, wherever it is, I can't just copy an axis like I can copy a plane. So that, I don't understand with that. But the thing is, you can just generate axes and everything. The key is the data is coming from somewhere else. Okay, we'll finish that off. I've got this cool little taper here, and I show the tool for how to do that in my thing. Okay, so let's say I've convinced you that there's actual value to doing this. Okay, how does that work? Okay, let's imagine this isn't here. And we don't even have to imagine that in a sense, because if we go to Insert, Tools, I sound dumb. Insert, yes, Part. So I'm in a part, and I go to the Insert Part menu. Now, when I click on that, it says what part, and let's say, we'll just go through an exercise here. Let's take the gull wing crossbar, and I don't even know, this is fairly old. This isn't even the new one. Let's get the newest one. How's that? There we go. Not cross. Yeah. I don't know. Whatever this one is. Okay, we're going to bring that in. Okay. I've told them that. And then I select over here, do I want solid bodies or surface bodies, axes, planes, coordinate systems? These generally get checked. I usually don't import material or of all that stuff. I typically don't use sketches for this kind of thing. I'm usually bringing in geometries. I might bring in a solid body or a surface body. In this case, I'm going to bring a solid body in from that because let's say for some reason I want to trace that in this part. And I've got locate part with move copy features. So I'll say, okay, let's bring it in. And then it pauses and then it says, oh shit, where do you want it? And you can tell this is an old failed part. And I can add a mate. And I'll just, oops. I'll go, this is that part, and I'll say, I don't know, UCS of the left riser strut to the origin of this, make them coincident, and align the axes, and add. Now, I'm just throwing this in here. It's probably not mated correctly. Oh, we can close that down. So now this crossbar component is in my part. We've got solid bodies within our part. There's two solid bodies. One is our currently working and one's the imported one. Well, that's cool. Here's our part, and I could leave that in there and have a multi-body part this way, or I could just sketch this and then get rid of it. I'm going to get rid of this right now. Yes. So there's that part of all this, okay? So that's what that's doing there. And that's how easy it is to bring this stuff in. And like I said, we got all this geometry. We've got coordinate systems that are defined in it. Let's go to the master part. Now, I can re-edit by going edit feature because this part is essentially being treated as a feature where I bring it in, right? So I can edit that and go to all those screens we just went through. But let's say I want to edit the part or let's say the configuration. I can go to edit external references, and up here I can change one of the three configurations of the handlebar setup that I've got there. Simple enough, and here's the in context references and things like that. But here I can change the configuration, but we're not going to do that. We're going to go and actually look at the part. So now I have to go edit in context. So that essentially is open part, like you'd be used to from a assembly. And here you can see I've created all kinds of geometry that helps describe this part. Because I do some calculations, let's just go to the pivot type area. We can look at that. And here are some XY coordinates and things like that where I'm defining some axes and things. So there's a lot happening with geometry here. Down at the bottom, I need a point for my UCS. Call it a UCS because AutoCAD burned it into me. But a coordinate system, you need a point as well as some other geometry like planes to define these UCSs. And these UCSs are awesome. Let's just show the UCSs. So I've effectively got a UCS for the end of the handlebar, the insertion point of the handlebar grip and the inserts, the struts themselves. These are for the rise bars, these UCSs. And why I'm doing that is I'm building this geometry, this whole geometry, and then I'm saying, okay, this point aligned just so, is how this other part is going to interface with it. And that way, when I put this whole master part into that part, I'm aligning that to the origin so that the origin makes sense. It's not out in space or anything like that. So UCS has become really important once you enter into a master part configuration. And then of course I do make a sketch here. This is the only 2 sketches in this one where I draw out the paragon binder facing either way, and then I produce a surface. Okay, so, and then the surface bodies are those 2. And those can come in. There aren't any solids here. There's just construction geometry. Okay, now you say, oh, Pete, there's no sketches. I've never worked without sketches. Okay, well, time to learn about equations. Okay, now, there are huge benefits, of course, with master part modeling, but what I discovered, because I was using a lot of equations here, and we can look at this, is a lot of equations. I think in the blog post I say I have 68 in the handlebar and, 61 equations in the handlebar and 226 for the frame. So essentially those are parameters or calculations that have come from that. We can go in and we can manage equations. And we can take a look at these equations. And you don't have to do this. There's probably other ways, or I mean, I know there are other ways of producing similar results without using so much math and equations. But just like when I'm making my fixture table, I want to take shortcuts. And on the fixture table, having a raster plane to build all my tooling on is a massive shortcut because I effectively don't have to construct everything every time. I just jump right in where I want to. Well, math is our friend that way too. And while you can create a lot of things in a sketch or by just building out construction geometry, you can also skip a bunch of steps and get a real high level of precision and accuracy. And I'm going to open up Excel here to show that these calculations, and we get into a lot of just, it's 3D trig, right? Or generally it's like a 2D trig, but we're solving in 3D space so we can get coordinates or dimensional shifts up from various things. But we have to define parameters. Like for building a set of handlebars, you can't just build a set of handlebars and be like the handlebar exists as a part, because it doesn't. It exists within a system. The whole bike is a system. So if you notice here, I'm actually bringing in, let's see, the frame information that's relevant to a handlebar, the head angle, the head tube length, the crank axis height, the front rim diameter, tire, all this, fork length, offset, how much sag. You know, in the modern era, we have to, and folks hopefully have read that work on mine, where in the new gravel type forks, the stanchion is not aligned with the steering axis. There's an angular shift, and that needs to be introduced into calculations to ensure precision. And so I have that in my math, and this is a mountain bike fork, so it's actually a 0-degree shift. So that's nothing we have to be concerned with. Up top, I have my handlebar geometry, like my sweep angle, my bar width, my sweep from the ground, that's within the handlebar, the inside bar end from intersection, and that's a goofball number for a number of reasons that are just, that's some legacy values coming in. But yeah, I'm bringing all that stuff in, and then I can skip a bunch of steps by doing some cool math. There's some input values here. It's hard to organize equations in SolidWorks. So rather than having all my input parameters at the start, I actually have to kind of bring them to a sensible area. If you notice, this is all the strut information, and here's all the frame information or something like that. And I don't count these as equations. These are just telling me what the value is within a certain thing. Like handlebar intersection y calculated is a plane that is D1, and it's referring to this. I could, rather than going to that plane in the feature tree, I could just change it right here, and that's why that information is provided. Oh, this stuff has to move up because this is not a that doesn't belong down here. I do like to keep everything above all that because that stuff doesn't matter. Anyway, a lot of interesting stuff, but if you've ever worked with equations, and here's an equation field being edited, now I can have them different values for different configurations. Like up here, if you notice, that's applying to just one configuration, versus down here, this calculation is applying to all configurations. Because of course that configuration, that's going to be true for everything because it just uses these values to calculate. So it can all be different, and we show our configurations up here. We can do all kinds of stuff. And I'm going to be filling this out more later because I've been building foundation recently. Every now and then we backtrack, build foundation, and then we extend until things get really messy, and then we have to go back and build foundation, and this process keeps continuing. I've been doing it for with bicycle design for the past 20 years or more, something like that. I've done a number of these processes to get to where I am. Okay, but when I do this, if I make an error, some of these are really long. Let's see how long this one is. That's not a very long one. This one, no, that's not long. Oh, this will be long because this is finding where to see how huge that equation is in the SolidWorks, and we can scroll through it and see just how much math is going on there. Blah, blah, blah. Big. There's a lot of shit happening. Okay. I store all this stuff in my master calculator here, and I have various stuff for frame design. That was just a quickie math thing. But we can look right here and see what that math looks like in Excel. Some things need to be cleaned up, but that's what's going on there. Okay, I need to clean that up. But big math, good place to store it, and then I can use it anywhere else. But like I show in the, actually, let's go to, right here. Like, you might have to go to a text editor, right? And this is often the way to do it, to bounce in between Excel, where you're storing a lot of this math, and going into a text editor. But here you can edit it a lot quicker and easier. There are some formulaic differences in form between SolidWorks and Excel, which don't make any sense why they'd be different. And there's also some logic stuff too, where unlike Microsoft's, is it Visual Basic? I can't remember. I wrote a blog post about the difference in some of the logic type stuff where SolidWorks conforms a little bit more to a, is it Python or C++ format for their logic rather than the Microsoft Visual stuff. So that's something to be careful of with a lot of this stuff. But the form for, like here, arctangent and square root, they're different in SolidWorks than Excel. So when you're importing things, or the naming of stuff, you have to change all that. Otherwise, an error forms in SolidWorks, and it won't tell you why. It'll just shit the bed on you, and then you're screwed. So that transition gets a little tough, but once you get it, you're good, and you just save it. We got that. Okay, let's cancel. Let's go back to these images. Okay, accountability. Okay, we're inserting the master part. These are how we chose stuff. That's how it looks in our screen. These are our equations. There's a text editor. That's how that works there. And there's our tool being used. So if I go down to the bottom here, like, so we've got that cool tool. There's a proof of, and this extends a little bit more into the tool that was made. So like we're maybe not talking about master. Oh, one last thing about master part and equations and all that. So people that know SolidWorks will know that there is a function where you can use table-driven parts and things like that, rather than going through the equations menu and things, and like I'm showing here. I've tried that in the past, and it is so terrible and works so poorly when you're just using it as a part and you're doing a table driven or an assembly and doing table driven, that I would never encourage anybody to do that. But one thing that I have yet to explore is by using a master part and doing table driven data into that master part, it may actually work out well, because this method saves a lot of processing time and does a lot of solving, so that you're not doing solving while you're modeling in the part or the assembly. You're doing your solving when you're dealing with the master part. So, and you don't do that all the time. Generally, it's maybe only a couple times during a design cycle that you'll have to jump into the master part and make changes or add more detail. And it's slow and cumbersome then, because it's just SolidWorks works very slow for some things and very fast for others. But that it may be that using a table driven setup would be like that. And I would prefer that, because like I say, I have all of my bike data on a table here and all my formulas and stuff. It would be so much nicer if I could just sit there and change a value in this Excel file, and then next time I open up SolidWorks, everything updates to what this file is. That would be really cool, and it may be fast enough using the master part method that works. So that's the kind of the next thing I'm going to after this, is seeing if that can actually be functional. But this is really cool. While it's in the fixture, while the tool, we're jumping back into the design of the handlebar tooling, because I actually got a chance to use it in the past week. Here's the parts, and I have a dummy hole saw or plug or whatever that I put in after my cut, and I actually removed the struts from the tool and deburr them and clean them and everything like that, get them all ready, and then I actually can use that to place the part back in so that it's aligned correctly, because and here's a jack that's used. So the tooling ball is used to find the zero coordinate of the fixture, and then I can move my cutter to the correct position. And then I have a jack here that ensures that the parts are entering the steerer binder at effectively the exact same point. Cool little jack thing I designed for this tool plate. And then you just pick it up from the mill and bolt it down to the welding table. And here I'm about to, I'm getting ready to weld next week and everything, so I'm getting all my parts done, and I just need to put the steerer holder up there, which is an interesting setup, kind of loosey-goosey, but it works great. But here it's like the same tooling goes right into here, and I'll pull this out of the way because that's just ensuring everything's right. Now, this recent week I posted this because everybody's talking about some stupid shit, and I figured I'd share this, but I have this media. It gets a lot easier to create these big assemblies when you have master parts. When all these parts are mated to that, and you can find errors. Let's see, I have some pictures of cutting the tools and how I design them. Here is the last round of tool that was done, and you can see I went from T-slot to a raster pin for different diameters. This is the old indexing system and little carriage that I made, and tools evolve. This is for a 16-degree back sweep. This is for an 18-degree back sweep, but the improvements are there. I will in the future improve the shape of the cart to match the model and everything, but I'm moving forward with design. This part is what really got improved on this last round, other than the sliding cart. You see these pins right here where I can make sure that that point is the same on both sides. I actually used a 300 thousandths gauge block to do the spacing, so it's like down to the thousandth. Cutting that taper on my handlebars, you see this. It's this interesting thing I haven't seen a lot of out there. It's an arbor for cutting the bent tube. Because I can't hold it in the lathe. Here's what's happening back at the headstock of the lathe, where I've got this bent tube coming up here, and it's being held by this arbor. And then I can cut a nice little taper at the end, like that. See, it's very slight, but one thing that really drives me nuts when I see glued together bikes or lugs or anything like that, and you've got a full section thickness at the transition area, it just looks so cheap and lame. Certainly if it's a printed part, there's no excuse for having it look that way. But here, even with a homogeneous tube, I've done that because it's that important, and that was a wild tool to figure out. You can see here we've got a 42-degree plane here that's cut, that is the handlebar sweep, because handlebar sweep is the main reference for all this tooling. 42 degrees. I'm zeroing out to that tooling ball that I use on my fixture, and essentially that's on the raster, and it sticks up 2.5 inches where the center plane is. And because, like I said, I did this calculator over here, I know that once I find that zero, I need to move my cutter 42. I don't know if you can see that, 42.81 millimeters from zero here, and that's where the cut will be, and that's mathematically correct. And yeah, you can get this through modeling, but I like calculators. I think one of the nice things that I talk about with Excel or whatever spreadsheet program you're trying to use is the ubiquity, that if I send a file to somebody in France and it's an Excel file or a formula that's formatted for Excel, they can use it. They don't have to have exotic solid modeling packages or have a high degree of programming proficiency or anything like that. Spreadsheets are really good places to do a lot of your work just because you can pass it on. We're seeing this setup. It's really cool. I mean, it's just Legos, and it's like, well, I bolt the plate here to a block from the welding system, and then I just clamp it in. I don't think do I show the digital protractor where I do the, I didn't get one of those pictures in there. It's for setting the angle, and then you can see that we're doing the cut right here. Boom, nice and rigid too. I mean, 16 millimeter steel is no joke. And you can see here, after I've placed my struts back in and they're deburred and cleaned, I've got my jack in, I'm checking everything, and I do 2 passes with this cutter, one for the main part of the lug miter, but then I move it away a little bit. I think on this one it was like 120 thousandths of an inch to make a second pass to give it that little extra back clearance to make up for that weird shape. And well, there you go. I'm hoping I explained this well, because this is complex and it seems like a lot of work, and it is some significant front side investment. Um, but for some of the stuff, it's really important to do. There's another thing about this master part is the propagation of changes. Um, you can think you're covering every one of your bases when you're working in a weird environment about going into a part and changing a parameter and changing it in the other part and changing it in the other part. But you could miss one, and that could be really expensive. And I know people that have missed a parameter, and it resulted them getting 3D prints that didn't fit brake mounts or something like that. And it was a real boondoggle because one thing got missed. And when you're using the master part, when you make a change, it will immediately, upon the next opening of that part, I believe, or if it's currently open, it'll change and update. But it propagates to everything that uses that master part information. There's some weird stuff that happens with SolidWorks. So if you are using in context mates or configurations or in context assembly references, I think that's the right term, in SolidWorks for an assembly, and you have a subassembly below that that's using in context subassembly references. I think at that level, if you're in the subassembly, it doesn't make the update. And it's either the first level of subassembly or the second, where an assembly-based in-context reference won't update. So if you change configurations, it will remain the subassembly at the configuration that it previously used, and it causes massive amounts of disruption. And I think that is something that catches people later on, and they wonder what they're doing wrong. And I certainly went down that road. I mean, that was probably 12 years ago where I was still trying to get that to work. And that's a huge problem. And that's when I shifted to starting to use equations in each file. But I had to make sure I updated every equation in every file. And now with the master part, I still use equations in construction geometry, but I'm only doing it in one file, and it propagates to the rest. So we have, let's say, a high level of insurance that any changes do get propagated. And I think a lot of people right now are maybe starting to play with in-context references, and that's going to start biting them in the ass. And I'm trying to show you how we look at it 10 or 15 years later so that you can save yourself. Okay, so I guess we're going to call that quits. So if anybody does have anything to say about this, whether they are CAD experts well above me and can add to this, please reach out and contact me. I'm including this documentation again on my website. And for others, it would be nice to find out who's applying some of these principles and maybe what they learned. Because like I say in this, where I think it was Ronen that talked to me first about master parts and using them. I'm in a vacuum in lots of ways. The way I do things is based entirely on me and me figuring out solutions versus me with a team of expert engineers that have worked in lots of different places, solving lots of different problems. So there could be better ways that I don't know about, and I'd love to learn them. I'm desperate to get better ways of doing this. But I did want to show so that I felt bad the last one. My accountability mechanism forces me to go back and fix this stuff. And now my setup's really good, and I'm really stoked. Um, cool. Well, thank you very much.